Good afternoon, everyone. And today I would be presenting the talk about the PLUTO code, which is a widely used astrophysical code by the astrophysical community. And today the focus would be on using astrophysical codes for high energy problems. The outline, the second slide, the outline of my talk will be as follows. The main motivation of studying high energetic astrophysical objects are the presence of large number of cosmic accelerators. The complicated physics that is involved in these cosmic accelerators requires us to use numerical simulations. The code that I will be describing, mainly the capabilities and the new features in order to study such objects, is the PLUTO code. And then I would actually describe the multi-scale nature of the problem that we have in hand and how we can actually address such problems using the simulations. In particular, I'll focus on three high energy astrophysical sources. That's the supernova, the knots from MHD Jets, and oblique shocks and relativistic flows. And finally, summarize my results. The main motivation, I think you must have seen these slides many times in this conference, but the main motivation is basically the observational fact that there is there's a powerful cosmic ray spectrum that covers a wide range in energy space, covering almost up to 9 to 10 orders of magnitude. This spectrum actually provides a challenge to the theoreticians to understand what are the origins of presence of such high energetic particles and where do they actually arise from. It is believed that the knee, which is actually at about 10 to the power 15 electron volts, up to the knee, most of the energetic particles are coming from the galactic sources, specifically from the supernova. Whereas beyond the knee, there could be the origin from the extragalactic space. And so, just to give you like a list of what are the accelerators, which are in the third slide, the accelerators which are responsible to produce such high energetic sources. In the galactic or nearby sources, the most important one is the solar, is the sun. The coronal mass ejection is also responsible to accelerate particles which are experienced on the Earth. Another interesting one are the late stages of the star when the star actually explodes into a supernova, producing a large amount of almost spherical shock that travels into the space. Along with it associated are the instabilities. Over here, in the third slide on the top left, you see a Tycho supernova, a composite image where you have the blue is the X-ray and the other emission from radio as well. These sources are responsible to accelerate particles to very high energy. And the important extragalactic contribution comes from jets from massive black holes, the supermassive black hole. Here you can see an image of Cygnus A, a fast collimated beam of plasma surrounded it with this shroud. And this shroud is essentially the radio emission that actually comes from this object. And most of these emissions are associated with high energetic electrons that are gyrating along the magnetic field lines and emitting its synchrotron radiation. Also, the extragalactic contribution may come from stellar mass black holes like the microquasar, and also from the Crab Nebula, which is actually which has a neutron star at the base. So all these objects do contribute and show presence of non-thermal emission and presence of high energetic particles. But to understand this complex physics, one has to implement them in a properly in a highly astrophysical code. So for this purpose, we have used PLUTO code. And the PLUTO code actually was conceived here in University of Torino by Andrea Mignone. And the code was actually designed in a modular fashion, has hydrodynamics, magnetohydrodynamics, and their special relativistic counterparts. The code basically is conservative and is finite volume based. It uses the Godunov flux to compute solve the hyperbolic equations. The code comes in both static and adaptive mesh refinements, and covers all three dimensions like 1D, 2D, and 3D, and supports all sorts of geometries, starting from Cartesian to polars, all sorts of regular geometries. The code is completely parallelized using the MPI library and written in C. However, the AMR part basically has some C++ extensions. And this code is widely used by the astrophysical community to do lots of problems, not only high energy physics, high energy astrophysics. Essentially, in the next slide, we have the equations which typically the PLUTO code solves when it is run with an ideal MHD setup. So these equations must be very familiar. So they are the mass conservation equation, which evolves the density. And these equations are written in conservative form, which are usually used by the code to solve. The momentum conservation and the total energy conservation, where E is the total energy and P is the total pressure, which are expressed below here. And in the middle is the induction equation, which is responsible for the evolution of the magnetic field lines. Along with that, you have a constraint that the del dot V has to be 0. So these are the ideal sets of equations which are solved by the PLUTO. However, for most of the astrophysical problems, ideal limit is very well and very fine. But in some cases, you may need to actually also incorporate additional physics. And PLUTO code already has features which can incorporate such additional physics. For example, to study accretion disk, you need viscosity because of the angular momentum transport due to viscous effects. And the viscosity has already been included. Along with that, you also have thermal conductions, both isotropic and anisotropic in presence of magnetic fields, which can be very useful to study solar plasma. In addition, you have magnetic resistivity, all the non-ideal MHD effects like the magnetic resistivity, Hall MHD, and ambipolar diffusion, which can be useful to study collapse of large-scale molecular clouds. In addition, you have radiative cooling and chemistry that may be responsible to study thermal emission from jets. And the most important in the new module that we have recently developed is what I'm going to be focusing today in this talk is about these Lagrangian particles, which are known as macroparticles. And as we go on, we will understand what are these macroparticles. In addition, you also have, I will go briefly over the module of cosmic rays, which is still in the preparation stage or in the preparation stage, and also dust. So as I mentioned before, this code has been used not only in the group of in Torino, where we expertise in studying relativistic jets and jets from stellar objects, but it's also been used by other communities to study, for example, the turbulence in accretion disk due to magnetorotational instability, or the star-disk interaction between the disk and the star, studying how the material actually accretes onto the central star, and also in studying of blast waves with to actually address the problems of supernova. Going to the next slide on studying particle acceleration in magnetized jets. As I mentioned, over here we actually do mostly simulations of relativistic jets. So here is a typical jet which is shown. It's of picture A. The image is of picture A. The central is a supermassive black hole. What you see in the blue line is basically the X-ray emission, the strong X-ray emission, which is actually focused. And the red shroud that covers this is the radio VLA emission. The focusing of these jets is usually believed to be because of the magnetic fields which are present. The toroidal magnetic fields actually confines these jets, forming this cylindrical structure. And the electrons, the high energetic electrons that are present in these jets are actually gyrating along these magnetic field lines and emitting synchrotron radiation. And this is essentially what we see in this emission process. So, apart from the synchrotron process, there are other loss mechanisms that are responsible. For example, inverse Compton, when the high energetic electrons actually interact with the CMB photon. Also, the adiabatic expansion of the jet causes to lose some energy. So if you do a very simple calculation that what is the amount of energy that are required for a 1 kiloelectron volt synchrotron radiation, you see that the energy of the electron is about 10 to the power 13 electron volts. And for typical magnetic field strength about 200 microgauss, the timescale of synchrotron cooling is about 30 years, which is extremely small as compared to the dynamical timescale. If there were no any additional energy input to the system, the electron would have cooled down completely and we wouldn't have seen any emissions to such a large extent. And therefore, this is one of the most crucial facts that one needs an additional energy input mechanism to give into these particles so that these particles are accelerated in situ inside these jets. There are three main modes of particle acceleration which are discussed in the literature. The first one is a diffusive shock acceleration, which is the Fermi first order process. Second is the magnetic reconnection that involves oppositely directed field lines or shear of magnetic fields to produce direct electric fields to accelerate particles. And then you also have turbulent acceleration because of the presence of turbulence. In this talk, I would be only focusing on the diffusive shock acceleration part. Going to the next slide about the diffusive shock acceleration. The basics of diffusive shock acceleration is in order to understand the basic, one has to look at this picture where the middle gray portion is essentially the shock. And the idea is that the energetic particle that enters into this shock is repeatedly scattered upstream and downstream many times, multiple times. And over each scattering, it basically gains energy which is proportional to its velocity of the flow. And as a result, ultimately, when the particle actually, after multiple scattering between the shocks, as it escapes the system, it essentially obtains a resultant power law, which has a power m given by 3r over r minus 1 in standard diffusive shock acceleration theory, where r is the compression ratio. So basically, the power that is attained by the particle after it crosses the shock is basically dependent on the properties of the shock, and mainly specifically the compression ratio. Also, we will see later on that it also depends on the orientation of the magnetic field line. So in this kind of acceleration process is widely used to study basically particle acceleration in such large scale jets. And they naturally, the main advantage is that they naturally give rise to power law spectral distribution. But to understand from the third point of view, like going into the real microphysics of it, we have modified PLUTO to actually incorporate the hybrid particle in cell like configuration, where the electrons are actually treated as massless inertialess fluid and highly magnetized, and they are being updated using fluid description. However, we also incorporate particles which are what we call as the active particles or the cosmic rays, and these particles are actually updated based on this equation over here, the update of cosmic rays, where the position of the velocity is obtained from the particle velocity, and the particle velocity is updated based on the Lorentz force that is experienced. However, there is also coupling between the particle and the fluid through the Lorentz force experienced by the cosmic rays, which involves the cosmic ray current. That is because of these charged cosmic rays move along with the fluid. And this cosmic ray, this Lorentz force actually comes into the momentum and the energy equation to solve the fluid. So that's where the coupling actually happens. Along with that, the electric field essentially has a component not only from the motional magnetic fields, the electric field due to motion of magnetic fields, but also this relative between the Hall-like term, which basically comes because of the relative drift motion between the electrons and the cosmic rays. And this is crucial because this kind of term is responsible to generate instabilities, the non-resonant instabilities like the Bell instability. And we go to the next slide where we see the cosmic ray driven instabilities. And these nonlinear instabilities are responsible to amplify the magnetic field line or magnetic field. And this magnetic fields, amplified magnetic fields act as scatterers in order to actually accelerate the particles. In order to demonstrate this, we did a very simple experiment with the PLUTO code where we actually, in the hybrid fixed formalism, where we actually have an LX covering 10240 points with about 10 to the power 5 ion inertial scale, and LY, which is basically up to about 1000 ion inertial scale. The magnetic field is along the x direction. In code units is 1. The velocity is actually going in the negative x direction with magnitude 30, and the density and the pressure are uniform and said to be 1. So what happens is when the fluid hits the conducting wall on the left, it reflects back, forming shocks. The particles are the cosmic ray particles with a Gaussian energy, focusing at the 10 times the shock energy, are injected periodically into this shock interface. And because of the motion of these cosmic rays, you tend to generate the instabilities as are shown over here in the magnetic energy. The images are actually only focused where the shocks are, and you can see how the particles are actually, how the particle motion is generating the magnetic fields, and these magnetic fields are essentially responsible, turbulent magnetic fields are essentially responsible to scatter the particles upstream and downstream, and thereby enhancing or energizing these particles. And so what you see over here is that the evolution on the left, you see the evolution of the initial energy distribution, which is a Gaussian, shown as a blue curve, how it actually expands to higher and higher energy and attains about 2 orders of magnitude over the course of time, about 3000 distance. But the point is, how effective can we actually use this method to study acceleration at very, very large scale? So this is essentially the microphysics that is involved. But the point is, can we actually incorporate such microphysics is the challenge because of the scales that are involved in jets. For example, here is a comparison in the next slide is a comparison of the physical scales of the jets. There you see that the typical length scales of these jets range from about kiloparsec scales, or even more actually. The jet radius for the AGN jets are about 100 parsec. These jets are actually relativistic in nature and are highly collimated as we saw in the images before. And this is mainly due to the magnetic fields. But also their emission is mainly dominated by non-thermal processes. So the point is that whether in the next slide, whether you actually can incorporate such microphysics in the scales. In the scales where you want to really simulate such large-scale features, specifically the multi-wavelength nature of the AGN jets. So here you see an image of M87, the radio image of M87 on the large scale is taken at VLA. You see a lot of turbulent features seen in this jet. But now if you actually focus in between these stars, you see that there is an emission of a small jet which actually comes out and has various knotty features, producing intermittent knots. These knots are actually also seen in a much more closer with VLA. The thing is that the simulation which we showed before about the cosmic ray instability producing this shock covers a very, very small scale as about 10 to the power 8 to 10 to the power 9 centimeters. Whereas the emission is, the observed scales are of the order of 10 to the power 21 centimeters. This disparity in the length scales is about 10 to the power 12 or so. And this is absolutely impossible right now with the current day computational simulations to actually resolve such large scale variance. And therefore one needs to treat the microphysics in a subgrid fashion manner in order to actually simulate the large scale flow. So this is one of the challenges that this kind of problems really face. Not only that, even from the simulation point of view, if one wants to simulate the jets right from the base to the place where it actually interacts with the interstellar or the intergalactic medium, that means covering a range of about 100 kiloparsecs or so, it is very difficult because here you see in the next image in the multi-scale nature, you see that on the top is a simulation of density, shown as the density in color and the magnetic field lines of the jet actually being launched from an accretion disk. And this kind of jet simulations are only responsible to study the launching process, where one gets information about the angular momentum transport and so on. However, if he wants to study the instability and the shocks that are produced at larger scale, one would need to study the jets from the nozzle point of view, where actually shown at the bottom, where you actually have jets being put at the nozzle with certain velocity, which are perturbed, and you produce actually these intermittent shock-like structures. And this is where each of these shocks are actually where at the very, very small scale do these microphysics of cosmic ray acceleration happen. So in order to actually break this scale difference, one would need to really create a bridge where one takes the simulations, the macrophysical quantities like the density, velocity, temperature, magnetic field strength from the simulations, and then provide some sort of a bridging factor which involves the physics of particle acceleration, or in stellar jets, chemistry, thermodynamics, radiative processes, so that one can actually extend these simulations in order to produce the observational features that are seen at very, very large scale. And also to reproduce the spectral emission, which are kind of observed in these large scales. So in order to do so, we have developed we have developed a Lagrangian particle module. In this module, what you do is the particles now are slightly different than the cosmic rays. The cosmic rays update was based on the electric and the magnetic field that it experiences from the fluid. Over here, the particles are actually, the difference is the particles are following the fluid passively. There is no feedback between the particle and the fluid. But these particles actually serve as a proxy for the unresolved microphysics that we actually saw. It's much more tricky when you actually want to simulate very large scale problems. So the update of these Lagrangian particles is a very simple update where the position is basically updated with the velocity, where the velocity is actually obtained from the fluid that is interpolated on the particle position. Note that the particle is distributed anywhere on the grid, and it may not be that the particle lies on the grid, and therefore one needs to interpolate the velocity from the center of the grid, which is usually where the velocity is defined, to the position of the particle. And this is mainly done using the weight functions, which are usually used in the PIC codes. So with this interpolation, what you see is over here is a nice image of Kelvin-Helmholtz instability. In the background color is the fluid simulation, which shows the vorticity in color. And you see that the formation of a vortex, and suspended on these vortex are these particles, which are actually the Lagrangian particles. And as expected, since they follow the fluid, they're actually following the particle streamlines and following the vorticity. So this kind of approach we will use in order to study the emission from large-scale jets and other astrophysical objects. Going to the next slide, about the macroparticles. So essentially, in order to study the emission process, what we essentially describe each of these Lagrangian particles as a macroparticle. A macroparticle is essentially, so that each of the white points on the previous slide represents a bunch of electrons or leptons, which are physically close in space but has a wide range in energy. And so basically each particle is nothing but a 1D momentum grid in energy, 1D energy grid in this space, covering from Emin to Emax, usually a very large band. And this distribution of microparticles, which are associated with each microparticle, are evolved based on this equation, which is the Fokker-Planck equation, which comprises of different terms. The term which involves del dot U is the adiabatic expansion or the compression term. The dij, which is a diffusion coefficient, is basically responsible for the second order Fermi effects, which are at present not included in the problem. The DPP, which is the second order Fermi effect, is not included. What is included are the synchrotron losses along with the inverse Compton and other losses that are responsible to lose the energy of these particles. And also what we have included is the first order Fermi process. So the subgrid information about the diffusive shock acceleration is included, where what we do is we actually track the particle as they move along the shock and estimate the compression ratio of the shock. And based on the value of the compression ratio, we update its particle spectra using the expression given over here, where the upstream distribution is updated with this Q parameter, and this Q actually is determined with the compression ratio of the shock. So every time in the flow at different shock strengths, the particle will have different spectral energy distribution. So the first test problem, or the first problem that we actually attack with such a kind of hybrid formalism using Lagrangian method is of supernova, and this is a non-relativistic MHD simulation. So supernova essentially shown over here are the Cassiopeia A images, where you see that this supernova shows emission in all bands, right from X-rays to radio, both in thermal and non-thermal emission. And they are important because they are believed to be the sources of galactic cosmic rays up to the knee, producing about 10 to the power 15 electron volts. The application that we have done is for the supernova SN 1006. It is basically a textbook case, and it was first actually observed. It is at a distance of 7,000 light years and was first documented by Chinese astronomers about 1,000 years ago from now. And the radial extent it has achieved now is about 10 parsec in the sky plane. The non-thermal X-rays are actually mainly due to synchrotron processes, and the inverse Compton are also believed to actually inverse Compton scattering of these synchrotron electrons are also responsible to produce gamma ray emission. Shown at the bottom are the composite image, and the green and the red are basically the VLA image of the supernova SN 1006. You can see that the emission is actually strongly peaked in these bright rims which are placed here, and so is also the X-ray emission. So we would like to understand that if our particle and fluid module Lagrangian can actually reproduce such kind of bright rim features. So in order for a simplified version of a test, there are various numerous models in 2D and 3D for such kind of supernova. But for our first simple application, we will use a simple 2D axisymmetric model in which the R and Z in cylindrical coordinates, the R and Z extends out to about 12 and 24 parsec. We have a very good resolution in order to simulate the fluid, and about 1 million particles, or about 10 to the power 5 particles are actually injected into this system. The initial density and the radius of the ejecta are all taken from these previous models, and we have used an equation of state which is of adiabatic nature. What you see over here is an image in density, which goes from 0 to 4, and basically peaking at the shock. The contact wave, this is basically the forward shock. The contact wave is actually, as you can see, very well unstable to relative instability, producing these kind of features. And they are very, very common in such kind of supernova objects, supernova simulations. And on the red are actually shown the magnetic field lines, which are initially placed along the Z direction. And as the shock moves, it basically curves along the shock. And these are essentially responsible for producing the emission, because if you actually have an observer which is not inclined to the line of, which is not inclined to the magnetic field, only the emission which is perpendicular to the magnetic field is responsible to which will be observed for such synchrotron processes. So we actually, in the next slide, what we see is that how the strong supernova shock translates in presence of Lagrangian particles, which are the passive tracers. So we have in 10 to the power 5 macroparticles in the ambient medium. And as you can see, as the particle evolves, these are essentially the compression ratio of these particles as these particles have passed through the shock. So they achieve a value of 4 or approximately close to 4, which is expected for a strong adiabatic shock. And because of this, you can see that the electron spectral index, which is the Q, which is used to update the spectral density or the spectral information, actually has a peak around 2.1 or 2, which is essentially what is expected from observation results. So if you see a single particle, if you just see how the spectra of the single particle evolves, initially we have an power law spectra, which is indicated by dark blue line. Since it's in the magnetic fields, it starts to lose energy. So this is what you see over here, with very minor, that you see the loss of energy due to synchrotron processes. And then when the particle is actually experiencing a shock, its energy the spectra becomes much flatter to the energy that it gains due to the diffusive shock acceleration process and achieves a flatter spectra. And after that, eventually it starts again to lose energy from cyan line to the red line because of the magnetic fields, the enhanced magnetic fields that are present inside the shock interface. So this kind of spectra are then taken and then post-processed in order to obtain the emission due to synchrotron processes. So essentially what we do is we actually convolve the spectra with the emissivity of a single electron to produce emissivities of a collection of electrons. And if you go to the next slide, here is a simulated emissivity in 2 different bands, because since the spectra covers a large energy band, we can actually see what are the emissivity in different frequencies. And this is what essentially we obtain. So we see essentially in the radio emission, you see that there is also these bright rim features. Note that these are just emissivity maps and it's still in 2D. And you see still bright rim features associated with the supernova shock. And along with that, you also see this, corresponding to that, you also have X-ray emission in these bright arc-like features. And so in a way, our model actually shows some sort of a qualitative comparison with the observations, essentially with the bright rims. However, in order to do a proper quantitative comparison, we would need 3D models, which are essentially what we plan to do in future. Coming to the next object is basically the kiloparsec scale radio jets. And ultimately, what we want to understand is that how the particles are actually emitting due to synchrotron processes in these jets. So here is an image, all our radio images of these jets. And these jets are actually very old, so that most of their activity is almost getting over. And so all these energetic electrons, which are actually present, will start losing energy due to synchrotron processes. And the spectrum, which would initially be a much more steeper, much more flatter, will actually reduce into a very steep cutoff spectrum due to synchrotron processes. And so in order to understand this, and also the emission, which are actually peaking at some of these knots and at the bow shock, we try to model such kind of jets using our hybrid Lagrangian and PLUTO code. In this problem, since we know that at such large kiloparsec scale jets, typically these AGN jets move with very mildly relativistic speeds. The Lorentz factor is about 1 or 2, about 1 and 2. And so in this problem, we are actually only simulating the normal MHD and not using a relativistic MHD, which is a valid approximation. So for this problem, we actually have the grid extent going from 3.2 kiloparsec to about 12.8 kiloparsec and has a good resolution. The radius of the jet is about 100 parsec at the nozzle, and the density of the jet is underdense as compared to the ambient medium, and the material is actually injected into the medium along with the particles periodically with a sonic Mach number of 4. The magnetic field is actually dominated by the toroidal field, which is true in most of these jets, and has a magnitude typically of the order of 100 microgauss. The particles are about are injected periodically at the base and has a power law spectra initially of e to the power -3 and covers a large range in energy band, about 6 orders of magnitude. So over here you see an image of the jet tracer shown in the color, where you can see definitely the formation of these Kelvin-Helmholtz vortices and also the bow shock which is actually present over here. And shown are the particles on the right. The color of the particles indicate the time when they are injected. So for example, the purple particles are the old particles which are there, and the green ones are the freshly which are injected into the jets. So if you take one of these particles and study the evolution of the spectra like we did for the supernova, you see that the initial spectrum, which actually has the power law, the distribution, will immediately cool down as it enters into the medium. So alongside the spectra, you basically see the trajectory of the particle. So the particle enters at about t equal to 26.3, and that evolves into a region which is highly magnetized, and as a result, it completely cools down due to synchrotron cooling. However, when this particle actually enters into this one of these internal knots, it gets accelerated because of the diffusive shock acceleration, and then when it actually is reflected back into the system, it again cools down periodically to a very, very small energy band. So translating this spectrum into emission, again like what we did for the supernova, you see that there are peaking in emission, especially shown by this green color at the knots of these jets, where these particles are really very well accelerated. Also, what you see is the emission green close to the bow shock, where there is a lot of acceleration due to the presence of shocks. And so this way one can understand that at these knots, diffusive shock acceleration could be playing a role. However, if you see the cocoon of the jet, you see that there is hardly any emission at 1.6 gigahertz. This is because all these particles have never experienced a shock and they have completely cooled down. So in that case, one would require additional acceleration mechanism in order to kind of keep up the energy of these electrons, even in the cocoon, which are consistent with observation. Also present in these jets. So this one was the last simulation was of the axisymmetric jet, and in the next slide we see that there are the jets are associated with large number of magnetic instabilities, which are of non-axisymmetric nature, be it kink instability or sausage instability. And this are translated very well into these observation features. For example, over here you see a case of 3C499. On the background you see an X-ray image and on the top you see basically a contour, white color contour, which are representing a radio jet which is emitted from this source. A zoomed in version is shown alongside, where you see the different features of these radio emission, and this radio emission is actually peaking along the jet, and it has this turbulent features at the base of the flow. Now, in order to understand such kind of features, one cannot use an axisymmetric setup. One would need to actually adopt to a 3D setup. And this is essentially what we are planning, what we are currently doing. And this is something which is in the production stage. In the next slide, we have extended the 2D axisymmetric setup into 3D. And here you can see the image on the left is basically the jet material which is being traced. The color shows the jet tracer. You can immediately see that this jet is actually undergoing a lot of magnetic instabilities and producing this turbulent jet-like structure. And along with that, like we did for the 2D simulations, we are also injecting particles periodically. And what we are interested is that we would like to see if the emission from these particles could actually reproduce the observations from these jets. But this is something which is the work in progress, and we would like to continue to do more and more 3D models to show more and more quantitative agreement with the observations. And the last problem that we are actually interested is is that of again a 2D problem, which is in order to study qualitatively the observations, is that when we go very close to the black hole. Now, when we go very close to the black hole, the speed of the jets becomes extremely high, or it becomes highly relativistic, and have Lorentz factors ranging up to 5 to 10. So in this kind of problems, we cannot adopt a non-relativistic module, and therefore we have adopted a relativistic module to study such kind of features. So the features that I'm describing over here is shown in these images for these two sources, 3C346 and 3C264. So in the 3C346 image, the background, again you see the X-ray. On the top, you see the contours of radio emission, which shows a V-shaped structure. So this is essentially attributed to the fact that these jets are interacting with the ambient medium and producing an oblique shocks. And these oblique shocks are responsible to produce such kind of V-shaped structure. And this is shown much more zoomed in the bottom plot. Also, when these jets interact with the ambient medium, on the right hand side for the case of 3C264, you see the polarization image due to synchrotron processes. These are synchrotron emission, they are responsible for linear polarization. And you see that how these jets are actually showing high degree of polarization where the flow interacts with the ambient medium, that is at the edges. And this is essentially what we try to understand as to how these particles are actually being treated at such edges. But as I mentioned before, in order to actually translate the microphysics of non-relativistic shocks to relativistic shocks, the system becomes much more complicated. Because again here, the spectral index or the spectral distribution after the particle crosses the shock still depends on the properties of the shock, like the compression ratio and also the magnetic field orientation. But here the difference is that the compression ratio cannot be estimated like in non-relativistic case just by taking the ratio of the densities. Over here, one needs to actually translate into a relativistic shock frame and then compute the compression ratio in that frame by estimating the upstream and the downstream velocity. So we, in this hybrid module, we have also incorporated this feature where we actually track the particle crossing the shock and track all the upstream and the downstream quantities and transform them into the normal incidence frame and then finally estimate the compression ratio. So shown here is the plot of the compression ratio for a planar shock problem, where we see that the compression ratio from the analytical and the simulated agrees very well. And also to note over here that the compression ratio varies between 3 and 4 for relativistic flows. In order to actually, so most of the simulations which have been done to describing emission from these jets always use a constant value of the spectral index, which is n equal to 2.3, and does not involve any, basically assumption is the Bohm diffusion, and the particle is actually completely isotropically distributed. In our case, we also try to study the dependence of the spectral energy distribution with the orientation of the magnetic fields. So when the magnetic fields are actually in the shock rest frame, when the magnetic fields in the lab frame, when the magnetic fields are parallel to the end shock, this normal to the shock, and the injection of the part of to the non-thermal. So the acceleration is much more efficient. Whereas when it is perpendicular. And for this kind of cases, we have actually adopted two different spectral indexes, which can be clearly seen from the next slide about showing how for different angles of inclination of the magnetic fields, you have different spectral indexes from the shocks. So on the left, you see basically the angle theta b is the angle between the shock normal and the magnetic field line. So in this case, it is the parallel shock. In the downstream case, and you basically have an initial steep power law spectra which gets come to very high energy and a much more flatter spectra. However, the same spectral distribution, initial spectral distribution, in perpendicular case is not efficiently accelerated to very high energies. And this is essentially crucial to study not only the emission, but also the polarization. And in order to compute the emission, I will not go into the details of the slide, but what is more important to know over here is that the emission that you obtain, the spectral density that you obtain, has to be convolved to the electron emissivity and also the relativistic effects due to Doppler boosting and other effects have to be taken into account in order to study such objects. But the most important point that I want you to take from this slide is basically the observed polarization degree and the angle of observation. So theoretically, and the frame of the shock, the polarization is about, for m equal to 3 is about 75%. However, due to relativistic effects, this polarization actually, the material gets depolarized and the polarization becomes about 0.55 or so. And this polarization index, the saturation, doesn't depend upon the value of the Lorentz factor, as you can see over here. It's almost the same. So we take this setup and apply in a very simple problem what we know as the slab jets or the shocks. Again, the setup is very simple. We basically have an underdense medium which is having a distance, it's in Cartesian coordinates, as a distance, a width of about 200 parsecs, and is underdense and has the same pressure as the ambient medium. And this material is actually injected or is in a periodic box. It's thrown basically with a Lorentz factor of 5. And as the magnetic field is much higher than what we saw before because these regions are very close to the black hole. And as a result, what you see is a development of Kelvin-Helmholtz instability because of the shear, velocity shear between the two flows. So here you see that the steepening of the Kelvin-Helmholtz instability and the color are basically the density and the streamlines are the magnetic field lines. So you see that the density actually forms this shock structure over a time, and eventually this shock builds up. So we also in this setup, we also put a lot of particles which are originally uniformly distributed in this setup. But these particles then ultimately are then treated in order to study the emission. And these are the simulated emission that you obtain. So if you actually fix the power law spectra, like has been done previously, you see that there is a lot of emission, especially coming from this V-shaped structure. There's highly emission, whereas if you take the power law which is dependent on the magnetic field orientation, the emission is reduced. But this is important because at this shock interface, the magnetic fields are highly perpendicular to the shock normal, and therefore one would expect that the shock injection, the acceleration is reduced, the efficiency is reduced, and as a result, one would have a much more steeper spectrum. Because of the steeper spectrum, what you see is that the polarization in this interface is much higher, as we saw that the polarization was decreasing. The degree of polarization was increasing with higher spectral indexes. So this kind of qualitative agreement has a qualitative agreement with what we saw from the images, from observations, where you actually have high polarization degrees at the interface of the jet. So finally, summarizing what we have done. The problem of studying jets and even supernova, high energy astrophysical sources with simulation is definitely a complicated one and involves a multi-scalar nature. The microphysics are are done at much more smaller scales, whereas the macrophysics happens at much larger scale. So we have developed a versatile hybrid particle module that actually, for the PLUTO code, that can actually somehow elevate this problem of somehow bring some sort of a bridging to this scale variance. However, one would need to have a proper subgrid formalism in order to study really and compare it with observation along with 3D simulations. But most importantly is that our applications to 2D shows qualitative agreement with observations, And also an important fact that the orientation of the magnetic field lines play a crucial role in determining not only the emission but also the polarization. And the final goal is essentially to apply these modules to build a full synthetic observatory so that one can actually compare simulations with observations for the upcoming telescope. Thank you.
Thank you, Dr. Vaidya. Would you like to accept questions?
Absolutely.
Is there any question?
In your slide title, Cosmic Ray Driven Instability, I saw that,
yes.
I felt that the shock was moving backwards with time. Can you explain to me why?
No, yeah, okay. So actually I should have told this. So actually the snapshot, if you see the scale, the snapshots are taken so that the shock is actually stationary. So basically we don't want so this is over time, you see that the snapshots are taken at different times. And of course the shock is moving forward, but we have only restricted our image so that the shock is approximately in the center of the image. So it's not moving backwards. So you can see.
Okay, so the frame is moving with the shock, you're saying?
Yeah, exactly.
Okay. Yeah, looks like.
Yes.
Okay, another thing is you're treating electrons as fluids, right?
That's correct.
Yeah, so what makes you assume that the electron Weibull instability will not play a role?
Well, I'm going to say over here, what we are interested is in a much, as you can see from the scales, these are like about 10 to the power 5 ion inertial scales or even more. At these scales, the important, so the thing is over here, for Weibull instability to happen, you need both the kinetic description for both electrons and ions or positrons in order to actually produce this Weibull instability. Over here, this is actually classic case for Bell instability, in which you actually have a hybrid formalism of electron and particle. And at this large scale, the electron pressure, the gradient of the electron pressure and the Hall terms are actually not important, and they are not actually featuring also in the electric field. Otherwise, you would have, if you see the electric fields from the Ohm's law, you have V cross B, the the Hall term between the cosmic ray and the gas velocity, but you also have the Hall term between ions and electrons, and also the gradient of the electron pressure. But these two terms are not important from the scales that we are interested in, because at these scales, these terms are much, much smaller.
Thank you.
If there are no more questions, we'll thank Dr. Vaidya for taking the trouble to come on Skype. Thank you, Dr. Vaidya. It was an extremely interesting talk. Thank you.
Thank you very much. Thank you.